and my partner, Emmanuel. Our project is a Monte Carlo simulation of a retirement investment problem. The core question is, does a retiree's 500,000 in savings actually last her lifetime, or does she run out of money before she dies? We'll walk through how we modeled this, what the simulation does, and what we found.
All right, so here's the setup. So we have a 60-year-old woman who's retiring on January 1st, 2027. As of January 1st, 2026, she has $500,000 saved up. Her remaining lifespan is uncertain, and we model it as an exponential distribution with a mean of 15 years. So she might live 5 more years, or she might live 30. So every January 1st, she makes a withdrawal to cover her living expenses. So she takes 40,000 the first year. The amount grows by 2.5% each year to keep up with inflation. And whatever money is left when she dies goes equally to her two children. So we're addressing the four questions. One, what's the probability she runs out of money? Two, if she doesn't run out, how much do her children inherit? Three, if she does run out, how long does that take? And four, she has the option to pay a one-time 20,000 fee to adjust a model parameter. Should she?
Now, here's what makes this interesting. Her investment return each year isn't a fixed rate. It's driven by a Q simulation. Every year, we first draw K from a geometric distribution with P equal to 0.25. K represents the number of servers in the MMKK also called an Erlang loss system. That means K servers, no waiting room, and any other customer who arrives when all servers are busy just leaves. Then we determine the arrival rate with probability K over K plus 1. Arrivals come in at 3 per minute for a normal day with probability 1 over k plus 1. They come in at 6 per minute for a busy surge day. We run that full queue for a full 8 hour workday and count X, the number of customers served, and Y, the number who were turned away. Then we plug those into this return formula R equals X over 4K minus Y over 2K, all divided by 100, which with a floor of -1. The critical thing to notice is when k equals 1, which happens 25% of the time, this formula always produces a return of negative 100%, completely wiping out the balance. That one fact drives almost everything in our results.
So what's our simulation approach? So for the simulation itself, we ran 10,000 independent replications. In each one, we draw a lifespan from the exponential distribution, then step through years one at a time. Each year, we apply that year's investment return to the balance, check if it hit zero, then subtract the withdrawal. We stop either when the balance runs out, depletion, or when we've passed the woman's lifespan, meaning she died with money still in the account. For the Q simulation, specifically simulating every individual customer arrival over an 8 hour day would be extremely slow across 10,000 replications. Since the queue reaches steady state in under a minute of the 8 hour day, we can use the Erlang V blocking probability formula to get the same result much faster. We validated this against a full event driven simulation on 300 runs, and the results matched almost exactly. Mean return of 0.266 versus 0.265. So the approximation is solid.
All right, results. So our question was the probability she outlives her money. Out of 10,000 replications, 7,834 resulted in the woman running out of money. That gives us an estimate of 78.3 with a confidence with a 95% confidence interval of 77.5% to 79.2%. So roughly a 3 in 4 chance she runs out. The reason is straightforward. K equals 1 happens 25% of the time, and every K equals 1 year in an instant total loss. Over a 15-year expected lifespan, hitting at least one of those years is nearly inevitable. We can actually verify this analytically. The probability of surviving without ever hitting K equals 1, given an exponential lifespan, works out to be about 18.8%, meaning about 81% ruin. Our simulation lands right in with that.
All right. So for Q2, if she doesn't run out, what do her children inherit? So the mean is 23.3 million with a 95% confidence interval of 4.5 million to 42 million. But that mean is misleading. The median is 758,000, which is far more representative. The distribution is heavily right skewed. The survivors are the people who got lucky and avoided every K equals 1 year. In those runs, a string of high K years generates enormous returns that compound the balance into the millions before she dies. Now, the median is the number you'd actually want to plan around. Each child would most likely inherit somewhere in the low to mid six figures.
Now, question three, for those who do run out, how long does it take? The mean is 3.28 years, 95% confidence interval of 3.22 to 3.34, and the median is just 2 years. When things go bad, they go fast. Most of the depletion cases are just the first K equals one. You're instantly wiping the balance to zero. There's a small right tail of cases where the balance slowly erodes over several years through modest returns that keep up with the growing withdrawals, but those are the exception.
All right. So the return distribution. So this plot shows why you can see the return distribution has a big spike at -1. That's the 25% of years where K equals 1. Everything to the right of 0 is the high return, K greater than 1 years. The model is bimodal by design. Um, by design years are catastrophic or very good. And which one you get is largely determined by whether K equals 1 or not.
Question four is the most actionable one. She can pay 20,000 upfront to change the geometric parameter P to anything between 0.22 and 0.28, should she? The key mechanic, since K follows a geometric with parameter P, the mean of K equals 1 over P. A smaller P means higher average K, which directly cuts the probability of a K equals 1 year. Since P of K equals 1 literally equals P, going from 0.25 to 0.22 cuts that catastrophic probability from 25% down to 22%. We ran a 10,000 replications for every candidate P with the fee already deducted. The results are in this table. P of outliving her money decreases monotonically as P decreases. Every step down in P is an improvement. The minimum is at P equals 0.22, where P outlives drops to 76.4%. Looking at the comparison chart here, the confidence intervals for P equals 0.22 and the base case do not overlap. So this is statistically significant improvement, not just noise. Our answer, yes, she should pay the fee and choose P equals 0.22. The 20,000 reduces her ruin probability by about 2 percentage points. The downside is her expected inheritance drops slightly because of her upfront cost. But when the primary goal is financial survivability, P equals 0.22 wins.
All right. So to wrap up, so for Q1, 78.3% chance she outlives her savings. Uh CI will be 77.5 to 79.2. For Q2, mean inheritance is 23.3 million, but median of 758 thousand is more realistic. Now, for CI, we have 4.5 million to 42 million. For Q3, the mean of 3.28 years to depletion when it happens, and median 2 years. Now for CI, we have 3.22 to 3.34. And for question four, the pay the fee, which choose P equals 0.22, statistically significant reduction in ruin probability.